committee for selecting me to present our talk today. It's supposed to be to attend the conference in Singapore, but for visa issue have been moved to come here to England in order to see you and welcome you here and enjoy your company as well. So the title of my talk today is revolving around some kind of the green protocol applications for the synthesis of organic chemistry. So the title is Novel, Efficient, Palladium-Free Catalyst for the Suzuki Carbon-Carbon Coupling Reactions. But just before going to my presentation, I would like to shortly give you some information about King Abdulaziz University in Saudi Arabia. So King Abdulaziz University is in Jeddah, where this city is a nice city like the Red Sea directly. You could find the Jeddah waterfront with the tallest fountain worldwide, and this is an old city. This is our university. It's the first Arabian university, as well as it's graded like 150 worldwide university. And our chemistry department is also have high rank between the departments in the worldwide. So this is just to differentiate between KU and KAUST, because some people asking about KAUST as well. Our group of research have been founded in 2004, just after I moved from Egypt and worked in Saudi Arabia, to establish the group for the surface chemistry and catalysis there. And we have very nice collaborator inside Saudi Arabia by KAUST, Sabit, and international collaboration as well by University College London, Imperial College London, Utrecht University in Netherlands, Friedrich Alexander University, Erlangen, Nuremberg. So this is just short group. Now return back to the outline of my presentation. We will talk about shortly about the carbon-carbon coupling reactions in general. Some statistical information I requested from my students to do as much as possible to give some information about to what extent we reach it for the carbon-carbon coupling reactions for time being. And again, I will give some information about Suzuki coupling exactly because this is the title of my presentation today. And the catalyst design, why we are thinking for a catalyst didn't contain palladium and what this catalyst exactly. And the catalytic test reaction, some characterization data and studying the sustainability of the catalyst, then going to the conclusion and outlook for my talk today. So first, I would like to coupling reactions simply in the organic chemistry, sketch up terms of the variety of the reactions using the metal catalyst for the formation of new compounds. Simply go to the reactor and forming biphenyl groups. It's classified into either homocoupling reactions where the two reactants are similar, or cross-coupling reactions where the two reactants are different from each other, more probably using the boron, organic boron molecules with alkyl halides. Since we remember all the history, but the synthesis of the carbon-carbon lab by Cole in 1845 with the synthesis of the acetic acid, many challenges and many professors starting to work in the carbon-carbon coupling reactions. We could remember also Heck, Negation, Suzuki already won the Nobel Prize in 2010 by their work in the carbon-carbon coupling reactions. Those people led others to think for going forward on synthesizing materials in the way of the complex organic one, which is especially for the Suzuki coupling reaction. And I will show in the next presentations, in the next slides, why especially Suzuki relative to the other kind of carbon-carbon reactions. Because by carbon-carbon coupling reactions, you could synthesize huge number of organic compounds by simple way, direct, so you can open the gate for the different applications for the people who are interested in the organic chemistry and organic synthesis. So statistical information, as I promised you, we try to hard to compare between the sweet coupling reactions to other coupling reactions. So we can see it's almost 49% of the carbon-carbon coupling reactions nowadays is made by the path of the sweet coupling method. Again, for the publications, you can see here the publications are growing up to, of course, 2019, which is reaching around 2051 publication, excluding, of course, American Chemical Society, as my students just this information they collect. So some information are missing as well. Then, why Suzuki reaction exactly? These are 4 main points that make Suzuki coupling better than others for the root of the carbon-carbon coupling. Number 1 is high radioselectivity for the reaction, high stereoselectivity, toleration of a broad range of functional groups, insignificant effect of the steric hindrance. Simply, you can go forward one by one. High radioselectivity, you can see here we have the organic poric, the boric acid organic compound, and this is the alkyl halide or the aryl halide. Simply, they could select it between, the coupling takes place between specific 2 carbon atoms, so you can directly select the halide, where is halide is present, so they can coupling from this point, not from the carbon number 1. This for the radioselectivity. Another example, if you have also 2 different halides, here we can compare between which one is easier to be removed from the ring itself. So according to the classification, you could find that bromide is easier to be removed than the chloride one. So the coupling takes place by carbon number 5. This is the order of the halides that should be like that, easier to remove the iodide than bromide and so on. Again, this more example, which bromine, this is inductive effect. In that case, you'll find that the bromine that between the nitrogen and sulfur, which is more affected by electron withdrawing. So according to the inductive effect, this coupling takes place from this side and not from the other side. many examples to show this radioselectivity. Again, for the stereoselectivity of the catalyst itself, here we could find some stereoselectivity. Again, collecting the bromine, forming the reaction. Here we have 2 possible products. One is produced by 82% yield, the other one is no yield. This means we have here stereoselective for one and only one product by 1 to 0, according to the coupling of this process. So you can select also the one and only one from the product, and this one is the stereoselectivity. Toleration of the broad range of the functional group, so whatever the bicyclo compounds or boroxine or pinacol, whatever the chain or the long chain of the boron compound is, you could use it easily for the formation of the coupling product. Insignificant hindrance, of course, during the process. So now we have to go to the catalyst design and why we are thinking for another catalyst instead of palladium. We can classify here the catalysts or the periodic table. If you look at the periodic table, we can find this group here, the precious metals, which is the copper, and the palladium, the platinum group, which is this group of the periodic table. They are using palladium, and of course in all the carbon-carbon coupling reactions they are using palladium instead of other elements. So why exactly palladium, and what are the drawbacks of using palladium? Palladium, for it's expensive for the economic point of view, it's not that favorable to be used as a catalyst. Second one is sensitive and requires additional reducing agent during the process. So we have to think for other catalysts could be related to the same group or similar or supposed to be similar, so that we think about nickel. But the question is, how we could select the nickel? As I asked my colleague before, if we select a certain element or a certain active site, you need to support this active site on a certain support and prevent as much as possible the depletion of this in the solution. So I mean, you need a sustainable active site on the support itself. We don't only to think for the nickel, but how to synthesize this nickel catalyst. This is the most important thing. So we have to return back again to the work of the layered double hydroxide material. In the layered double hydroxide material, which is mainly consists of cationic sheets made up of divalent cation, original magnesium hydroxide, could be replaced by trivalent cation, which is aluminum trivalent. Once you substitute the divalent cation magnesium by aluminum trivalent cation, you have extra positive charges on the cationic sheet that should be compensated by some anions in between the cationic sheets in the gallery itself. So the challenge now is to try to synthesize a catalyst by replacing the divalent cation, which is magnesium, by nickel in the cationic sheet. It's some kind of thinking like you need some basic sites, so you are using the clay material, the hydroxide material, as well as you adding nickel and retain the nickel in the structure of the cationic sheets, so you could prevent the depletion of this nickel later on the solution. That's how we thought. So series of the catalysts have been synthesized in our lab using co-precipitation method, but using ultrasound irradiation during the co-precipitation. From our experience, ultrasound irradiation during the synthesis of the material could affect its nano size. It affects more the nano size of the material, so we could see later how would the nano size of the material of our material have been obtained upon preparation under ultrasound irradiation. So we synthesize many catalysts. Start by just replace 1:1 nickel, nickel 1, magnesium 1, aluminum 1, then increase the percent of nickel on expense of the magnesium 1.5 to 0.5 to 1, and then completely remove magnesium from the story and adding nickel instead of magnesium in the structure. Not only this, these are the precursor of the material. Then we make a reduction at 200 degrees. This is of course part from huge catalysts have been synthesized and tested before. What I'm presenting today, just apart from the story, which is after many trials for the reduction and the reduction temperature and so on. So I have now as synthesized layer double hydroxide dried samples and reduced samples very specifically at 200 degrees centigrade. So we need now to make catalytic test reaction using the iodobenzene, which is alkyl halide, and the substituted chloric acid using different nickel aluminum and nickel layer double hydroxide catalysts, but these are the conditions of the reaction. This means we tried the reaction without microwave irradiation and make classical method. We did not get nice results, so we moved to the using microwave irradiation. After different tests, selected 300 watt, 140 degrees centigrade, and the reaction carried out in 30 minutes. In presence of potassium carbonate, dioxane, and water. So all of these are the conditions for the reaction. In order to obtain the product, the results obtained reveal that if we compare between the three catalysts to the presence of the catalyst, we got nothing in absence of the catalyst. In the presence of the dried catalysts, in compared to the reduced one, so we can see here the first catalyst only 31 yield% in comparison to the reduced form. The second one is 55 in comparison to the reduced form, and the best catalyst was the catalyst when we completely replace magnesium by nickel, and was 99% yield. So first of all the catalysts showed some activity. The best one is a nickel contained catalyst without presence of any of the magnesium. So we make generalization by changing the aldehyde, the halide radical. So we use different substrates, iodobenzene, bromo, chloro. The yield was the best for iodine, of course, which was expected, was easier, as I said before. Second, bromine. Third, chlorine. And then we calculated the turnover frequency for the reaction according to this equation, which is the number of mole of the product over number of moles of the catalyst by the time of the reaction in hour. So it's high turnover frequency using this method for the preparation of biphenyl compounds. Now we have to understand why that happened, what exactly happened for the catalyst. So XRD tells us we have the layered structure completely synthesized, because at 2 theta equals 11 you have the layered material. But if you compare between the three catalysts, you could find that here there is a decrease in the peak height at 003, which is the C direction, and an increase in the A to B direction. And this could give us some information about the precipitation of the nickel, not only in the form of nickel layer double hydroxide material, but we have nickel hydroxide 1, which is alpha nickel hydroxide, as had been confirmed later in other characterization. X-base measurements tells us about how much nickel are on the surface. So you could find around 97.7 nickel divalent isolated are on the surface of the catalyst. So we have nickel now like dispersed on the surface of the cationic sheet in the form of nickel divalent. 10 measurements, high resolution 10 measurements show that also the catalyst with high catalytic activity has the smallest particle size distribution. Surface area measurements didn't show that it's the best. No, the surface area is not high, although they all have the same isotherm. I mean the same model of the isotherm, unimodal distribution for almost mesoporous materials, but of lower surface area than the higher one. Could be the decrease in the surface area, as I said, due to the precipitation of nickel hydroxide out of the sheet itself in the form of alpha nickel hydroxide. Again, the stability of the catalyst is very important in order to prove that the catalyst could be work after the reaction. So make a filtration, washing the material again, reuse the catalyst many times. So we can find from the data obtained that it's almost sustainable after 5 runs. This decrease or appear decrease in the catalytic activity is due to the loss of the mass of the catalyst itself. You are using filtration process. So once you're using filtration, washing, reusing it again, of course you will lose mass of the catalyst. Some organic contaminants, because you have the layered material, you couldn't exclude that the presence of the intercalation of some of the organic materials inside the gallery between the cationic sheets themselves. So the tentative mechanism of this reaction could be summarized in the form of oxidative addition. This is to the metal, which is the nickel one, then transmetallation and reductive elimination at the end of the story. It's like the classical Suzuki coupling mechanism reaction. So I'm going now to the conclusion and outlook. So in this study, nickel double hydroxide material were prepared by co-precipitation method under ultrasound irradiation. The isomorphic substitution of magnesium divalent by nickel divalent ions was proved by XRD. All the investigated nickel layer double hydroxide material exhibited favorable catalytic activity towards two carbon-carbon coupling reactions. The dried as synthesized nickel containing catalyst has the highest catalytic activity, and could be related to the high content of the surface nickel species and small particle size of the catalyst. The results obtained claim the catalytic efficacy would correlate to the nickel content more than the resisting. I forgot to tell you, testing the resist using Hammett indicator, showing that our catalyst is not basic as we expected to have. Different alkyl halides have been, of course, tried for the carbon-carbon coupling. The sustainability of the catalyst were proved. Now we have a catalyst which is palladium-free, could be able to substitute other palladium catalysts in the Suzuki carbon-carbon coupling reaction, which is very important. And this work has been published already for the Chemistry Select is just published. And I would like to thank my student. She did all of that work, PhD student, my former PhD student, which is staff member now at the university, and Professor Ilham, which is a co-supervisor for my student, and Dr. Nisreen Said, my wife, and the person who introduced me to the family of the organic sciences. So in order to go and support her of doing organic sciences, I fall in love with this organic part. So this is part of our work and not our main part. We are more interested in the gas phase reactions, catalysis, and so on. Like you. Thank you very much for your kind patience.
We have time for one question.
Yes. Of course, I'm expecting this question from you. And by the way, Angelo Vaccari is the father of the clay science. Anyone who makes citation for layer double hydroxide,
clarify that we start with the E dot aside, but not in logo with me.
Okay.
Considering the previous discussion. Now, just a comment very shortly. This similar cartridge was used in collaboration with Montpellier for the hydrogenation of the nitrile, and the two factors are hydrogenation capacity and basicity when you have magnesium in it.
Yes.
I think that in your case it's very important hydrogenation and the weak acidity, very weak acidity on nickel. You agree on this?
Yes, I'm agree with you. Totally agree. Thank you very much.
Okay, thanks again.
From our experience, chance.
Step back.
Okay.
Project that.
Okay.